Okay, we'll start today's session with the definition of power, which we have actually seen earlier also in the concept of virtual power theorem. But anyway, since it's a part of this chapter, let's understand this once again. So the definition of the quantity power. So the instantaneous power delivered by a force equals to the instantaneous rate of work done by the force with respect to time. So power equals to rate of work done with respect to time, the instantaneous rate of work done. Okay. Now, in time dt, the work done by that force is F dot ds, where ds is the displacement in the time interval dt. Hence, this can also be defined as F dot ds by dt. And since ds by dt is the instantaneous velocity, we have this final formula. So power becomes the instantaneous power becomes the scalar product of the force with the instantaneous velocity. Just make a note of this definition first. Okay, so the dimension of power becomes dimension of force multiplied by velocity. So that becomes and the unit power is watt, standard international system. So 1 watt equals to 1 Newton meter per second, or that's the same thing as 1 kilogram meter square per second cube, or that's also the same thing as 1 joule per second. Whereas the CGS unit is ergs, where 1 erg equals to 1 dyne centimeter per second, or sorry, the CGS system is erg per second. So 1 erg per second is 10 raised power minus 7 joules per second. Cookie. Yeah, Viraj, it is dyne centimeter per second. See, it is force multiplied by velocity, na, dimensionally. So dyne is the CGS unit of force. Okay. Only thing is this should be erg per second. It's dyne centimeters per second. Now 1 dyne centimeters, the same thing as 1 erg. Okay. Now there's also an old British system of unit in which we define unit in of this in horsepower. So this is outdated. We don't really use it, but it's used in automobile industry. So 1 horsepower is equal to approximately 746 watts. It's also called British horsepower. Anyway, so let's look at a quick example to understand this. So you have a block of given mass which is sliding down an inclined plane which has coefficient of friction 0.5. So this block was at rest at time t equal to 0 and its mass equals to 5 kilograms. So find the instantaneous power delivered by the weight, the frictional force, and the normal reaction at the instant t equal to 10 seconds on the block. Take g as 10 meters per second square. Okay, so there are a number of ways we can do this question, but easiest way is to first of all use the direct result from friction and Newton's laws of motion that we know, that the acceleration of the block down the inclined plane will be how much? It will be g into sine theta minus mu cos theta. So in this case, it will be 10 into sine 37, which is 0.6, minus friction, which is 0.5, into cos 37, which is 0.8. So this will become this much. So it will be 2 meters per second square. That is the acceleration. So therefore, at t equal to 10 seconds, the instantaneous velocity will be 20 meters per second. So now we know this, that at t equal to 10 seconds, the block is somewhere here and its instantaneous velocity is 20 meters per second. So now we have to just understand the forces. So mg is like this, kinetic friction, that is mu mg cos theta, like this, and normal reaction is like this. So this angle is theta. Okay. So the power delivered by mg will become mg dot product with the instantaneous velocity. So that is mgv cos 53, because you can see the angle between the instantaneous velocity and the gravitational force will be 53, because this angle is 37. So this angle is 53. So this will be equal to the weight, which is in this case 50 newtons, into the instantaneous velocity, which is 20, into 3/5. So that's becoming 600 watts. This is the power delivered by mg, the instantaneous power, at t equal to 10 seconds. Similarly, the power delivered by friction will become minus mu mg cos theta into the instantaneous velocity. As you can see that friction is acting at 180 degrees with respect to this. So the dot product will result in the minus sign. So let's write it in more detail first. So it will be frictional force is dot product with velocity. So that will become minus of frictional force into velocity. So that is minus mu mg cos theta into the instantaneous velocity. So that is minus of 0.5 into 50 into cos 37. So that's 4/5 into the instantaneous velocity, which is 20. So minus of 400 watts. This is the instantaneous power delivered by friction. And instantaneous power delivered by normal reaction, you can see is 0 because n is perpendicular to the instantaneous velocity. So this becomes the final answer. Just make a note of this, people. Yeah, Shikhar, I'll take you back to that. This is the part about horsepower. So horsepower is the same thing as British horsepower. So it was old part of the old British system of units. That's why it's sometimes also called British horsepower, particularly on automobile industry. Okay, so hope this question is clear. Okay, now anything that is defined as, okay, Shikhar, anything that is defined as a rate of change, we can also define the average rate of change for that. Just like, we define average velocity as average rate of change of displacement with time, whereas instantaneous velocity is instantaneous rate of change. So like that, we can also define the average power delivered by a force. Okay, so the average power delivered by a force F, okay, in time, let's say delta t, the total interval of time delta t. This will be defined as the average rate of work done with respect to time. So average power will be defined as work done upon total time. So that is F dot ds integrated divided by the time interval. So I mean the better way to understand it is just this, that it is total work done by the force F in that time interval delta t. So that is integration of F dot ds from whatever initial to final position in that delta t. So let's look at a very simple example to begin with this in this. So note down the definition first. So small body of mass 2 kg is projected vertically from the ground at t equal to 0 with initial vertical velocity of 60 meters per second. Find the average power delivered by gravity or the weight during its upward motion. Take g as 10 meters per second square. So during the time the object is going up, for that time interval, we have to find the average power delivered by mg. So now see, we can understand this question this way. So t equal to 0, we have projected it from the ground with an initial velocity of 60 meters per second. So we know that from kinematics, we understand that it will reach a highest point at u by g, that is 6 seconds, when its velocity will become 0. And this height it will climb is u square by 2g. So that will become 180 meters. So during this time, what is happening is that as the object is going up, the gravitational force on it is acting vertically downwards. So during the upward journey, that is 0 to 6 seconds, you can see the work done by gravity will be minus mgh. So that is minus of mass of the object was given to us as which was the mass now 2 kg. Okay, so minus 3600 joule. Yes, very good, that's correct, Aditya. So that's correct, the average power will become minus 600 joules per second or watts. Okay, so note this down. Now we'll also discuss a couple of tricks that we could have used here to make the whole thing simpler. Okay, so now see here, one more thing we could have used is that, okay, we know that at the highest point, in this case, speed is 0. So kinetic energy becomes 0. And initially, speed is u. So the kinetic energy is half mu square. So we know that work done by mg is change in kinetic energy. So we could have also directly used this, that the work done by mg is minus half mu square. That is minus half of 2 into 60 square. So this is the shortcut we could have used, that this is becoming minus 3600 joules. So instead of calculating height and all that, we could have just said this case, because there's only one force acting on the body, and the time is u by g, because final velocity is 0. So that is 6 seconds. So okay, so that's one little trick that we could have used. So this is the concept of average power. Okay, Durgesh, done with this? Okay. Let's discuss another quick sum. So this time what we are doing is, from the ground we are projecting something with an oblique projection. Okay, instead of a vertical projection, we are projecting something obliquely, like this, with an initial velocity of 50 meters per second at an angle of projection of 37 degrees. A body of mass 5 kg is projected at t equal to 0, as shown. So take the acceleration due to gravity to be 10 meters per second square. So we have to find the instantaneous power delivered by gravity at the instant t equal to, so we'll take two instants actually, t equal to 3 seconds and t equal to 5 seconds. We'll also calculate the average power from 0 to 3 seconds. Yes, that's correct. So you can see that the instantaneous velocity, which is Vx I cap plus Vy j cap. In this, Vx is equal to Ux, which is U cos theta, which in this case will be 40 meters per second. But Vy will be Uy minus Gt, which is 30 minus 10t. Okay. So at t equal to 3 seconds, the instantaneous velocity you'll see will just become 40 I cap. Okay. So from that you can see that power delivered by mg will be 0 because mg is along the y-axis. Okay, so mg is perpendicular to the instantaneous velocity, whereas at t equal to 5 seconds, you can see the instantaneous velocity will become 40 I cap minus of 20 j cap. Okay. So the instantaneous power delivered by mg will become plus 1000 watts. So basically for the projectile motion, what's happening is this is where it is at t equal to 3 seconds, having that horizontal velocity of 40 meters per second. Whereas it's somewhere here at t equal to 5 seconds, having a velocity like this. So at this point of time, power delivered by mg is 0. At this point of time, power delivered by mg will be positive because it's an acute angle between the two. Now for the second part, average power. Samaj, check out the B part. I have given you the answer. Okay. So the second part, the average power, we can also do this way. Work done by mg will be minus mgh, where h is this maximum height. That's one way we can do this. Okay. Okay. Or we can do one more thing, that the work done by mg is the change in kinetic energy. So kinetic energy at t equal to 3 seconds okay, whereas kinetic energy at t equal to 0. So the change in kinetic energy is okay. So that's another trick that we can use to find the work done. Anyhow, so hope this question is clear. So this is about instantaneous and average power. So it's not really related to work energy theorem directly, it's just a separate quantity. Now let's come back to the concept of potential energy and work done. I told you that we'll discuss some more tricks and relations used related to that. So back to work energy theorem, okay, and we'll discuss about the relation between the internal conservative force and potential energy in more detail. So you already seen the definition that change in potential energy is negative of work done by internal conservative force, or minus of F internal conservative dot ds. So suppose we have a one-dimensional system. Suppose we have that. So our force is just along the x-axis, and our displacement is also along the x-axis. So the above definition becomes that delta U is minus f dx integration, or du is minus f dx. This becomes the definition that for a small displacement of dx I cap, or basically just a displacement of dx, the change in potential energy du is minus f dx. This becomes the definition. So now the inverse of this we can say is that the internal conservative force is minus du by dx. So this is the internal conservative force in terms of the potential energy in a 1D system along the x-axis. So we say that internal conservative force is equal to negative gradient of potential energy. So in this, the operator d by dx is called gradient, just like the operator d by dt is called rate of change, because this is with respect to time. So it is called rate of change, whereas this is with respect to position. X is a position coordinate now. So that's why it is called gradient. Okay, so note this down and we will see some concepts related to this. Yes, I have explained gradient over here. This operator is called gradient. Differentiation with respect to x, that operator is called gradient. So the word definition becomes that internal conservative force is negative gradient of potential energy. Yeah, Durgesh, I have explained the definition here. Just write this down. There's nothing more. Just write this formula down. This is gradient. You know how to do differentiation with respect to x, so there's nothing more to explain. Okay, so let's understand this with an example. So the potential energy for a particle moving along the x-axis given by the formula okay, where U is in joules and X is in meters. Okay, finish writing that first. Come back to this question. Okay, so coming back to this question, so we are given this sort of formula here for potential energy. Okay, now assuming no external force and no non-conservative force acts on it, that means only internal conservative force acts. Given the mass of the particle, find its acceleration at the position x equal to 2 meters. We have to find both direction and magnitude. Okay, so understand the question fully first, then we'll discuss about how to solve this. Okay, so let's start with this and let's understand. So in a 1D system along the x-axis, if the internal conservative force is Fi cap, okay, then this F is given by minus of du by dx. That is, internal conservative force equals to negative gradient of potential energy. So in this case, the internal conservative force will have a magnitude of negative of differentiation with respect to x of this formula. Now you know that differentiation of 1 by x is how much? Minus 1 by x square. So this will become this will be the force, where F is in newtons, x is in meters. So therefore, we can understand that at x equal to 2 meters, the force has a magnitude of, or the force is 5 newtons along the positive x-axis. That is, the internal conservative force is plus 5 I cap in newtons. And now we know that the net force acting on the body is equal to the internal conservative force, because it was given that external force is absent, non-conservative force is absent. There's only one kind of force acting, which is the internal conservative force. So the net force acting on the body only is 5 I cap in newtons. Therefore, the acceleration is the net force divided by mass. So it has an acceleration of, we are taking the mass as 10 kg. So 0.5 meters per second square along the positive x-axis. Okay, so please make a note of this properly. Then we'll understand more things about this. Okay. How did we get this? It just comes from the reverse of this definition, na beta? See, you're defining delta U as negative of work done by internal conservative force. So that means du is minus F internal conservative dot ds now. So in 1D system, in a situation which is one dimensional, this is becoming minus F dx. This. So this relation's reverse is this now, that F is minus du by dx. Okay. So that's why in a 1D system, the relationship between internal conservative force, here F is the internal conservative force, and the potential energy is that it is negative gradient of potential energy. So that is the definition we have used now. So it's like this definition that F is minus du by dx is the reverse of that earlier definition, that delta U is negative of work done by the internal conservative force. Okay, now next point, very important. Okay, so I know that RTPS students have exam from 9 o'clock, so I'll just wind up this point within the next 5 minutes for them. So this is very important. So definition of equilibrium point. In a closed system. So closed system means what? A system with only internal conservative force. Okay, that means the net external force plus non-conservative force should be 0. So only internal conservative forces means that change in kinetic energy plus change in potential energy is 0, or there is conservation of mechanical energy. In such a system, an equilibrium point is the position at which acceleration is 0. That means the internal conservative force is 0. Okay. So for a closed system, this becomes a definition of an equilibrium point, because there is no external force. The sum of external force and non-conservative force is 0. So only internal conservative force is the net force. So an equilibrium point is a point where acceleration is 0, but acceleration is coming from which force? Only the internal conservative force. So internal conservative force should be 0. Okay. So in a 1D system, in a 1D, what we call closed system, with F external 0 and F non-conservative 0. Okay. Equilibrium position is at F equal to 0, where F is the internal conservative force. So in other words, du by dx equals to 0. Okay. So in a 1D system, In a 1D closed system, equilibrium point is where du by dx is 0. It means that the potential energy versus x has a local maxima or minima at equilibrium point. So in terms of graph theory, it means that if this is your potential energy versus x graph, then suppose at this point we have a local maxima and at this point we have a local minimum. So here what will happen is that the equilibrium points for this graph are at x equal to x1, where potential energy has maxima, okay, and x equal to x2, where potential energy has minima. Okay. So this is an important concept to remember. Just make a note of this first. Okay, make a note of this, and the Ramshed Thakur students can leave for the exam after noting this down. Okay, so let's see some problems related to this concept of equilibrium positions. But before we come to problems, the most basic example of this is if we have a spring mass system on a frictionless horizontal surface. We know that it's a closed system because there's no friction, and mg and normal reaction are balancing each other. So the net force acting on the body is only the conservative spring force. So we know that for such a system is on a smooth surface, at some point of time, if the speed of the block is v and the state of the spring is a compression or extension or whatever be the case, in this case it's like this. You know that for this system, half kx square plus half mv square is conserved, or the change in kinetic energy plus change in potential energy of the spring is zero. So this is an example of a one-dimensional closed system because only internal conservative force acts on the body. The net external force because of mg and normal reaction is zero, and there's no non-conservative force. Okay. So for this system, we can see the definition of potential energy is half kx square. So if you look at the potential energy graph versus x, you can see that it's a parabolic graph like this. So the potential energy has a minima at the point x equal to 0. So U has local minima of U equal to 0 at x equal to 0, whereas it has no local maxima. So that implies here that the system has a single equilibrium point, and that is at x equal to 0. So that means the acceleration of the block is 0 only at a single position, which is x equal to 0. So this is the sole equilibrium position, only equilibrium point for this system. Okay, so make a note of this standard example. So spring mass system like this has a single equilibrium point. Which we can interpret in terms of this new concept we have learned, that at any equilibrium point in a 1D system, in a 1D closed system, that is, the potential energy graph should be having a zero slope. So that means it should either be having a local maxima or a local minima. So basically we are making use of this point that equilibrium implies that the net force should be zero. So in a closed system, it means that minus du by dx should be zero. So that means the potential energy graph should have zero slope at equilibrium points. That means zero slope means there are positions where there is either local maxima or minima. Okay, so let's look at another system, another example of a system. So a 1D system, okay, along the x-axis with only conservative force, that is internal conservative force, acting on a particle of mass m has potential energy given by the formula U is equal to ten x to the power 4 minus 5x square, sorry, minus 20x square, where U is in joules and x is in meters. So find the position or positions of equilibrium for this particle. Calculate the values of potential energy at equilibrium points. And also find the particle's acceleration at x equal to 2 meters. Mass of the particle is suppose 2 kilograms. Okay, work this out quickly. Okay, people, let's look at the conclusion of this question. Yeah, very good. Let's understand the first part. So for equilibrium, for the first part, acceleration has to be zero, which means the force has to be zero, which in this case means du by dx has to be zero. So that means differentiation of this term this has to be zero. Okay. So 40x cube minus 40x has to be zero. So we can take 40x common. Okay. So we get x equal to 0, x equal to 1, and x equal to minus 1. We get three equilibrium points. These are our equilibrium points. So there are three positions of equilibrium. Okay, so some of you have missed out one of the roots. And you can see that the value of potential energy at x equal to 0 is 0. Value of potential energy at x equal to 1 is 10 minus 20, so minus 10 joules. The value of potential energy at x equal to minus 1 is also minus 10 joules. Okay, now as far as the third part is concerned, we want to find the acceleration of the block at x equal to 2 meters, at x equal to plus 2. And for that, we'll make use of this formula again, or from this, the value of force that we can get by du by dx and the mass. So we can see that the potential energy means that the force so you can write that as 40x minus 40x cube. This is the value of force. Therefore, at x equal to 2 meters, Okay, so that means the magnitude of the force acting on the body is 240 newtons, and direction is along the negative x-axis. Okay, so that means that the acceleration of the body is 120 meters per second square, and direction of acceleration is along the negative x-axis. Okay, so this is the conclusion of this particular question. So I'll just minimize this once more for you. So this is the important concept here today, the relation between potential energy and internal conservative force. In a 1D system. This concept, okay, and in a closed 1D system, equilibrium, which means that the net force should be zero, implies that the rate of change of potential energy or gradient of potential energy should be zero. Okay, so we'll conclude today's session here, people. Wish you all the best, and continue working on problems from work by energy. I'll send you an additional list of questions from H.C. Verma as well as your module now, which you can attempt in addition to the questions I had given last time. And in the next lecture, we will discuss some of the doubts from those examples for application of work energy theorem, both from H.C. Verma and from the module.